In the previous two sessions, we had an introduction to missing data. So, we discussed when a statistical data contains a missing data, in the sense that one or more of the cells of a data matrix has no value in it, and then we discussed what are the general ways of dealing with missing data. We also discussed the model based techniques to deal with missing data. So, how to construct the likelihood for missing data by using a missing data indicator. In this session, we would be dealing with the complete case analysis for missing data as well as the available case analysis for missing data. We would take an example and we would estimate what is the estimated value for the population mean as well as the population variance or variance covariance matrix when one or more data is missing. Complete case analysis for missing data. Suppose there are n subjects with an expected p measurement per subject, but there might be some subjects which might contain less than p measurements. So, here we would discard any subject with ni, where ni is number of observations for the ith subject is less than p. Then we have a set of complete cases denoted by NCC. So, the complete data response looks like NIC, that is for the ith one, is I runs from 1 to n, I, Ni equal to P is equal to summation I runs from 1 to n, an indicator of whether Ri is 1, where Ri is Ri1, Ri2, Ri-Ni. Now, here an estimate of the population mean mu is mu hat Cc, which is equal to I runs from 1 to n, capital I, that is the indicator of Ri equal to 1 into yi star by I runs from 1 to n, indicator of Ri equal to 1, which comes down to I runs from 1 to n summation of the p cross 1 vectors with component yi observed and any arbitrary value for yi miss, and that is represented by yi star. So, basically yi star for all those i's where we have at least ni measurements divided by NCC, where NCC represents the number of complete cases. Similarly, sigma hat Cc comes out to be yi star minus mu Cc hat into yi star minus mu Cc hat transpose, but the sum is over all those products, all those yi's for which the condition is satisfied, the condition being that Ni is equal to P, and the divisor here in this case is NCC minus 1. Now, there is a result that if the data is MCAR, that is missing completely at random, then the complete case estimator is an unbiased estimator of the population mean mu, and the complete case estimator for the sample for the population variance covariance is an unbiased estimator of the population variance covariance. So, expectation of mu hat Cc, the proof is that the expectation of mu hat Cc is expectation over the term 1 by n Cc summation I equal to 1 to n, I Ri equal to 1 into yi star, that means all those yi's which satisfies our condition. And if we just follow the steps are provided here. So, it leads to the fact that the expectation turns out to be mu. So, we can say that a mu hat CC is an unbiased estimator of the population mean mu, provided the data is missing completely at random. We can have a similar proof for the variance covariance matrix also. Now, the advantage of this approach, the complete case approach, is that it is easy, but the problem is that it is not fully efficient and it is not applicable to data if it is not missing completely at random. Available case analysis. For the available case analysis, what happens is we can define a mu j hat and sigma I j hat of the same form, but this time we are keeping an indicator vector of Rij equal to 1 into Yij star. That means we are only including all those j's. So, we are including the subjects or the cases for the subjects where the condition is satisfied, Ni equal to P condition is satisfied. And then we have the estimator as written here of mu j hat and sigma I j hat. But the problem here is that each estimator is based on a different set of subjects, because this is dependent on the j's. Similarly, we can it's dependent on the i's. Similarly, we can define covariance of sigma j j prime, and also we can see that it is dependent on the i's. So, mu j hat star is equal to mu j hat is based on I such that Rij equal to Rij prime equal to 1, and here rho jj prime comes out to be sigma jj prime by root over sigma ij into sigma ij prime. Now, it does not guarantee the fact that the rho jj prime would be, or the correlation between the jth and the j primeth observation of the ith value satisfies the condition that it is between -1 to +1. The advantage of available case analysis is that it is more efficient than the complete case, but it is biased and sigma hat may not be positive semi-definite. So, we want sigma hat to be positive semi-definite, but here we cannot guarantee that sigma hat would be PST. Now, one more idea in this context is factoring the likelihood. So, if we ignore the missing data mechanism and think that L theta given y observed is a complicated function, but let psi, which is a function of the theta, is an alternative parametrization, and phi is a one-to-one monotone function of theta. So, then it is possible to write L phi given y observed is equal to L1 phi 1 given y observed plus Lj phi j given y observed. So, this phi can be distinct parameters such that the joint parameter space of phi, which is phi 1 to phi j, is the product of the individual parameter spaces for phi j. J runs from 1 to capital J. So, here L phi given y observed can be maximized by maximizing Lj, which is phi j given y observed separately. So, instead of maximizing the entire likelihood, we can go for piecewise maximizations of the part of the likelihoods. For example, we can maximize L1 phi 1 given y observed plus L2 phi 2 given y observed, so on and so forth, and we can maximize L phi given y observed. Now, let us consider a case for bivariate normals. Now, consider a bivariate normal sample with one variable subject to non-response. yi1, yi2, the vector follows IID bivariate normal, mu equal to mu 1 mu 2, sigma equal to sigma 1 1 sigma 2 2 sigma 1 2 sigma 1 2 are the off diagonal elements. So, sigma 1 1 is the variance of y 1 and sigma 2 2 is the variance of y 2 and sigma 1 2 is the covariance of y 1 y 2, and here I ranges from 1 2 up to n. But assume that there are an extra p minus n univariate observations for y I 1. That means y I 1 is a p dimensional vector, whereas y I 2 is a n dimensional vector, or in other words p minus n observations of y I 2 is missing. In such a situation, how are we going to estimate mu and sigma? Now, we can factor the likelihood in terms of this, that y I 1 y I 2 given mu sigma can be written as f of y, or the it's basically the likelihood of or the density of y I 1 given mu 1 sigma 1 1 into the density of y I 2 given y I 1, that is the conditional density of y I 2 given y I 1, also beta 2 naught dot 1, beta 2 1 dot 1 and sigma 2 2 dot 1, where beta 2 naught dot 1 is mu 2 minus beta 2 1 dot 1 into mu 1, beta 2 1 dot 1 is sigma 1 2 by sigma 1 1, and sigma 2 2 dot 1 is sigma 2 2 minus sigma square 1 2 by sigma 1 1. Now, because it is a bivariate normal distribution, the density of y I 1 given mu 1 sigma 1 1 follows normal mu 1 sigma 1 1, and the conditional density of y I 2 given y I 1 beta 2 naught dot 1, beta 2 1 dot 1 and sigma 2 2 dot 1 follows a univariate normal with the mean beta 2 naught dot 1 plus beta 2 1 dot 1 into y I 1 comma the variance being sigma 2 2 dot 1. Now, given beta 2 naught dot 1, beta 2 1 dot 1 and sigma 2 2 dot 1, we can always estimate what is mu 2, what is the relationship between mu 2. So, mu 2 is beta 2 naught dot 1 plus beta 2 1 dot 1 into mu 1. Similarly, sigma 1 2 is beta 2 1 dot 1 into sigma 1 1, and sigma 2 2 is sigma 2 2 dot 1 plus beta 2 1 dot 1 square sigma 1 1. So, my theta here is mu 1 mu 2 sigma 1 1 sigma 1 2 and sigma 2 2. Note that if I know all this, I would be able to specify my mu and sigma, whereas phi here is mu 1 sigma 1 1 beta 2 naught dot 1 beta 2 1 dot 1 and sigma 2 2 dot 1. Because of the principle of factoring, I can factor the likelihood into two parts and I can maximize this 2. So, I can maximize f y observed given theta by telling that f y observed given theta is f of the product of I runs from 1 to p f y I 1 given mu 1 sigma 1 1. So, mu 1 sigma 1 1 is coming from the first term of the factorization, while beta 2 naught dot 1, beta 2 1 dot 1 and sigma 2 2 dot 1 comes from the second form of the factorization, which says that y I, the conditional density distribution of y I 2 given y I 1 follows a univariate normal. So, maximizing the first product gives my ML estimates for mu 1 sigma 1 1. Maximizing the second product gives the ML estimate of beta 2 naught dot 1, beta 2 1 dot 1 and sigma 2 2 dot 1, and hence I can get mu 1 hat and sigma 1 1 hat, which are the ML estimates of mu 1 and sigma 1 1. Similarly, I can get beta 2 1 hat 2 1 dot 1 hat beta 2 naught dot 1 hat and sigma 2 2 dot 1 hat. So, once I get beta 21 dot 1 hat, beta 20 dot 1 hat and sigma 22 dot 1 hat, I would be in a position to get the estimates of mu 2 hat, sigma 22 hat and sigma 12 hat. Then I can use the estimated values, that is mu I 2 hat is equal to y 2 bar plus beta 21 dot 1 hat y I 1 minus y 1 bar. So, this is nothing but the predicted value imputed from the linear regression of the observed y I 2 on observed y I 1, and using this idea of prediction from the imputed value of linear regression, we can have the imputed values of y I 2. We would be doing an exercise in R where we would take bivariate data with some observations missing, and we would see how we can compute the missing observations. So, in today's session, we learned about the complete case analysis and the available case analysis in context to missing data. We also learned about how to factor the likelihood and use maximization on the individual terms, so that instead of maximizing the complete likelihood, which is a complicated function, we can maximize individual functions, individual likelihood functions, and get the estimates. We also use this idea while estimating some missing values in context to a bivariate normal distribution. This idea would be followed up later after we are through with the theoretical parts of missing data, where we would see how to write a code and implement this factorization technique in R.